Hello, welcome to the Section 8.1 video lecture. I am Dr. Scott Spaniel, your instructor for statistics at Morton College, here once again with another video lecture. So we're about to enter into the third portion of our course. The first portion was chapters 1, 2, and 3, descriptive statistics, where we talked about how to basically describe a sample or a population using either graphs or statistical analysis. In chapters 5, 6, and 7, we talked about probability. And now in chapters 8, 9, 10, and 11, we're going to talk about how to use probability and descriptive statistics to do inferential statistics. So this is the idea of taking sample data and using probability to guess at, not guess isn't the right word, to take a statistical analysis and come up with where we think the population would be based on the sample results and what probability tells us. So in chapter 8, we're going to start out by looking at the distributions of the sample mean and the sample proportion. These are the graphs we're going to use along with probability to figure out where we think the population falls. So if you go ahead and take out your chapter 8 handouts if you want to follow along, or you can just take notes on paper and pencil. But remember, with all these videos, we should be taking notes just like we were in class. And we can find these handouts either in our Blackboard course or on my Math Lab course, depending on your course setup. And we're going to start looking at section 8.1, the distribution of the sample mean. So the sample distribution of a statistic is a probability distribution for all possible values of the statistic computed for a sample of size n. The distribution of the sample mean, x bar, is the probability distribution for all possible values of the random variable x bar computed from a sample of size n from a population with a mean of mu and a standard deviation of sigma. So suppose that a simple random sample of size n is drawn from a large population with a mean mu and a standard deviation of sigma. The sample distribution x bar will have a mean of mu sub x bar equals mu, and the standard deviation of x bar will be sigma over the square root of n, the standard deviation of the sampling distribution of x bar. Sigma sub x bar is called the standard error. So the idea here is that if you were to calculate every sample of a certain size and find its mean and standard deviation, and then find the mean of all of those and the standard deviation of all of those put together, what you would end up with is a distribution that had a mean that was the same as the original and a standard deviation that is proportional to the original based on the square root of the sample size. So the closer to the bigger your sample size gets, the smaller your standard deviation is. So another way to think about that is the larger your sample size is, the less it deviates from the population. The less error you would have built into the system, right? Because with really small samples, there's a lot of chance for error, for you to deviate from the mean. But with really large samples, there's a lot less chance of that. So let's look at what that looks like. So to give you an idea of what we're doing here with these, let's look at a very small population. So let's just look at the population of, let's just use 3 numbers. So let's say our population was the numbers 8. Well, actually, let me do some even simpler numbers for doing what I'm going to do here. Let's say our population numbers were 6, 12, and 24. Okay. So what we could do with those is we could use ClassCalc to find the mean and the standard deviation. I mean, we could do the mean of this pretty easily, but the standard deviation is a little trickier. So we could do, let's just do stat mean of 6, 12, and 24. So that's 14. And we could do the standard deviation of 6, 12, and 24. Okay. Although I'm not as concerned about the standard deviation here because our population is not large enough for us to do that part. What I'm more concerned with is this part right here. Okay, so this has a mean of 14. So what the sampling distribution should happen, according to that, with this mean, is that if I find what we want to do to find the mean of the sampling distribution is we want to find all samples of, let's say, size 2 from this population, right? So all those samples would be 6 with 12, 6 with 24, and 12 with 24. And then if you find the mean of each of these, so the X bar for each of these, so the mean of the first one would be 9, mean of the second one would be 15, and then the mean of the third one is 18. Okay? What this says at the top is that mu sub x bar should equal mu. So this mu sub x bar should be 14. So to find that, we do 9 plus 15 plus 18 over 3. Okay, and when we do that, we do indeed get 14. So that just shows you that this kind of works. Now, it's not, I can't do the standard deviation because our population isn't big enough, but that's the general idea of what we're looking for here. Okay, of what we're going to be doing. You've got your population, you find every sample of a certain size, and then you find their means, and then you find the mean of those means, and that's what we're looking at, is we're looking at what happens if I try and find the mean and the standard deviation of each of these. Okay. And I could show you, we did already say this, but if you look at the standard deviation for 6, 12, and 24, it was 7.48. If I do the standard deviation of while my formula won't work, I can show you that the standard deviation of these means is smaller, right? It's 3.74. So it's a lot smaller than this one. So when we look at these, our standard deviations are going to be smaller. So the way we do those calculations in general for large populations is the mean will be the same as the original, so that would be 80. And then the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of the sample size, which in this case, 14 divided by the square root of 49 is 2. So that's the idea of what we're going to be dealing with here to get down to these. So why don't you go ahead and take a moment, pause the video, and find the mean and standard deviation for the sampling distribution with these parameters and sample size. Okay, so now that you've had a chance to try it, let's try it together. So mu sub x bar is just going to be whatever mu is, so that's 27. And sigma sub x bar should be 6 divided by the square root of 15. So let's just do that here in the calculator. 6 divided by the square root of 15, which is 1.549. Okay, so that's the idea of what we're going to be looking at here. Now, where this is going to be useful later on is when we're doing things, when we're trying to decide if a sample, if the population has changed, or if we want to know what's the range around our sample result, would we expect the population to fall? This is really important anytime there's an election. They tell you the polling data with a margin of error. That margin of error is computed using normal curves. And they're computed using normal curves under this assumption of the sampling distribution based on the sample size and the data they found in the sample. So what we're doing here is we're building up to being able to do things like do margin of error, create what are called confidence intervals. So there's a couple of things to keep in mind here. First of all, if a random variable x is normally distributed, the distribution of the sample mean x bar is normally distributed. Okay, so if your random variable is normal, so is the distribution of your sample mean. Okay. So if your data is normal to begin with, then you don't have to worry about anything. However, if your data isn't normal, the central limit theorem can help us decide that our distribution will be normal. So regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. We assume that the distribution of a sample mean is approximately normal when n is greater than or equal to 30. Okay? Look at an applet that will demonstrate this central limit theorem idea. So the idea here is no matter how weird your original distribution is, as you start to increase the sample size, it will become more normal, more and more normally shaped. So like here, if I increase this is a fairly uniform distribution. If I increase the sample size from 1, which is just the data, to 3, I'm already getting a pretty normal shaped graph. Okay, and if I increase it all the way up to 30, then I get a very normally distributed graph. Even if I pick things that are very, very skewed, like this one. If I draw the original, it's very skewed. It's nowhere near normal. If I start to increase it, it starts to get more and more normal, but it's still skewed on the right side. Okay, and if we keep increasing it, the closer and closer we get to normal, until eventually at 30, we get a normal distributed graph. Even something where like it's skewed in both directions. Like there's a hump on both sides. Right? So that's still a little, with only a sample size of 4, that's still a pretty weird looking graph. With 10, we're getting pretty close. With a 19, we're even closer. And with 30, we have a normally distributed graph. So the idea behind the central limit theorem is if you get your sample size large enough, then the distribution of the sample means will be normal. And in pretty much every case, we can assume that once we get to 30 as a sample size, we're good to go. And this is one of the reasons why a lot of your the problems, a lot of times when this gets applied, when they do actual sampling, you have very large sample sizes. Part of the reason why is to make sure the central limit theorem is applicable. So let's look at an example of dealing with these type of things. So a simple random sample of size 12 is obtained from a population with mu equals to 64 and sigma equals to 17. What must be true regarding the distribution of the population in order to use the normal model to compute probabilities involving the sample mean? Assuming this condition is true, describe the sample distribution of x bar. Okay, so first things first, what has to be true in order for this to be mean? Well, one thing is n could be greater than or equal to 30, right? That would meet the central limit theorem. Is n greater than 30? No, that doesn't work. So we need another way. Well, that gets us back to this first theorem up here at the top. And it says if the random variable x is normally distributed, then the distribution of the sample mean would be normally distributed. So since the central limit theorem doesn't work here, we'd need the population, the random variable x to be normally distributed. Okay, so if that was the case, then we'd be good to go. So let's assume we are. If we are, then we can use our definitions back here for the mean and standard deviation. So that's what they mean by describe the sample distribution. So mu sub x bar would simply be mu. And sigma sub x bar would be sigma divided by the square root of n. So in this case, 17 divided by the square root of 12. So we can just put that in our calculator here. And we get 4.907. Okay. So once we've done that, now the question is, assuming the requirements for normality are satisfied, determine the probability of x bar is less than 67.3. So there's a couple things going on here. One, this is normally distributed. 2, we know how to find the probability of things that are normally distributed, right? We can use the normal curve and find the area under that curve. So if we're dealing with this situation, let me get rid of all these extra things I've got in my calculator. What I can do is a normal distribution, which you can find in the menu, or you can just type it out, right? Go to Stat, Distributions and Plot, Normal Dist, and then put in your mean, which we found to be 64, and your standard deviation, which was 17 divided by the square root of 12. And I would always type it out like I just did here, because what you don't want to have happen is you don't want rounding errors. So type out your square root. And then I can zoom in on it. Oh, that kind of zoomed in weird. Let's try that. Okay. Well, let's just back out. Oh. Whoa. Something weird is going on here. Let's just try typing it in and see if that makes this not as screwy. So maybe we are going to round. Okay, yeah, that worked out better. I don't know why it was being screwy there when I tried to do it. Because those are the same value. It must just add too much going on. So yeah, go ahead and plug in the rounded off number. That's fine. And then we can do our probabilities by using CDF just like we did in the last section, in section 7.2. So this would be 67.3. Okay. And so the probability of having a mean less than 67.3 would be 0.749. 4 if we go to 4 decimal places, which is pretty standard on the homework and stuff, so that's what I'll try and do. Okay, so that's x's bar is less than that, and then if we want to do x bar is greater than that, we get, so x, this time we're doing to the right, so 65.2, and that got us a probability of 0.403. Okay, and so now the question is, well, what happens if the sample size increased to 20? So all that's going to change is our standard deviation. Let me try this one more time. Now it's giving me the same answer. It's just looking super weird. I don't know why it's doing that. But let's just try changing this to 20 now. Okay. It's still looking weird. Okay, so let's do that calculation separately, and then I'll plug it in. So 17 divided by the square root of 20. Okay, so that now takes our square root down, our standard deviation down to 3.801. So now for 65.2, when n equals 20, I get 0.376. And if we do the other one, x is less than 67.3, we get 0.807. 4. Okay, so here are the answers we got. So what do you notice? Well, this one, the probability went up, and this one, the probability went down. And if you look at this one, you'll notice the mean is in that, but with the other one, the mean was not. Okay, so what happens to the probabilities as the sample size increased? Well, one of them went up and the other one went down. And the one that went up was the one where the mean was in the region we were finding the area of, and the one that went down was the one where the mean was not. So now let's look at some applications of this. Okay, so that's the idea. Let's look at some applications of this. So the most famous geyser in the world, Old Faithful, in Yellowstone National Park, has a mean time between eruptions of 85 minutes. If the interval of time between eruptions is normally distributed with a standard deviation of 21.25 minutes, answer the following questions. What is the probability that a randomly selected time interval between eruptions is longer than 95 minutes? So that's the probability that x is longer than 95 minutes. So notice the word mean didn't get mentioned anywhere in this problem. So this one we would do exactly as we were doing them before. So let's just get rid of everything here. So we can just put in our mean and our standard deviation just like we were doing in chapter 7. Okay. So there's our graph. Okay. So we can find the probability that a randomly selected one was greater than 95. Right? Is longer than 95 minutes. So we just plug in x is greater than 95, and that's a probability of 0.3190 if we round to 4 decimal places, right? Because this 9 becomes a 10, which makes this 8 into a 9. What is the, so that was the first problem. So that's what we were doing in chapter 7. So now let's see what happens. What is the probability that a random sample of 20 time intervals between eruptions has a longer mean than 95 minutes? So notice we're now doing 20 time intervals and we're looking at their mean. So that's what's going to start changing this. So for this one, we'd want to do normal distribution. The mean stays the same, remember, but now we're going to take 21.25 divided by the square root of our n, which is 20. Okay. Which is just not graphing right. So let's try this again. And then I wanted to try it one more time, but let's just try calculating this separately. So the standard deviation divided by the square root of 20, which is 4.7516. Okay, and so first of all, what you should notice is our graph got a lot skinnier and a lot taller because it still has to have the same area, but the standard deviation got a lot smaller. Okay, so you can already see that when I'm looking at a mean time between eruptions of 95 minutes, that we're going to be a lot smaller probability, right? Because 95 is still over here where this purple region starts, but now we're only going to have this line that goes on the bottom. So if we do CDF of 95, right, it's the same region, but look how much smaller that region is because it all got sucked in because the standard deviation is smaller. So the probability that a mean would be greater than or equal to 95 minutes is 0.0177. Okay, like that, because it's a smaller region. Okay, so what would you expect to happen if we increase the number of time intervals to 30 instead of 95 minutes? So if we want to do the probability of x bar is greater than or greater than 95, but now we want to have our sample size get bigger. Well, let's try that. So we've got our normal distribution again. This time 85 is still right, but now we're going to do 21.25 divided by the square root of 30, which is 3.8797. Okay. And we can see from the graph that it got even taller and narrower because once again the standard deviation is smaller, so our graph is less spread out, and so this area over here on the far side should get even smaller, right? So 95. And so now we're down to this area get even smaller in here. So that's 0.0050 if I round to 4 decimal places. Okay. So what effect does increasing the sample size have on the probability? Well, it makes the probability smaller in the tails. Right? It's sucking the area up into the middle, so the probability is getting smaller in the tails. So what might you conclude if a random sample of 30 time intervals between eruptions has a mean longer than 95 minutes? Well, that would be highly unusual, right? That probability is less than 5%, a lot less than 5%. So you might conclude that the mean time between eruptions has changed from 85. Okay, so we might assume that this number is wrong now, that 85, a mean of 85, is no longer accurate if we were to get a mean like that, because it's highly unlikely that our sample would give those results. And that's how we're going to use this in the future for what's called hypothesis testing. Okay. So to finish off this section, I just want you all to practice doing the same thing. So go ahead and turn to the next page, page 5, and practice doing these probabilities using this new standard deviation. Okay, so now that you've had a chance to trial these, let's go ahead and just go through the answers together. So we're going to start over with a new normal distribution, right? So normal distribution with a mean of 266 and a standard deviation of 16 days. So that's our original. So what is the probability that randomly selected pregnancy lasts less than 260 days? So that'd be X is less than 260. And so we get a probability of 0.3538. Now suppose that a random sample of 20 pregnancies is obtained. Describe the sampling distribution of the sample mean length of a human pregnancy. Okay, so because the original data was approximately normal, the distribution would be approximately normal, because it's not big enough to assume that on its own, but because the original data is approximately normal, we can assume the sampling distribution is, with a mean equal to the population mean of 266 and a sample standard deviation equal to 16 divided by the sample size. So 16 divided by the square root of 20, which is 3.5777. Okay. So then what is the probability the randomly selected sample of 20 pregnancies has a mean gestation period of 260 days or less? So, right, we need to set up a new normal distribution based on the first one where we have the same mean, but the standard deviation is now our new standard deviation, which is 3.5777. Okay, we can see it there, and if we zoom out, we can see just a normal curve where everything's getting sucked in because our sample size is bigger. And then we can do the same calculation, but it should be a much smaller probability, right? Because we're in a much smaller curve. So in this case, the probability would be 0.0468, right? If we have a sample size of 20 pregnancies. And now we can continue to increase it, right? So what if we increase the sample size to 50? So we use 16 divided by the square root of 50. We can plug that into a normal distribution with the same mean and this new standard deviation, 2.2627. Okay, so we've got our new graph, and it's going to have an even smaller probability, but we can try that out. What's the probability that it's less than 260? And now it's gone all the way down to 0.0040. And so what might you conclude if the random sample of 50 pregnancies resulted in a mean gestation period of 260 days or less? You might conclude that the population mean had decreased. Okay, so that's the idea. So the big takeaways from this section are that you can still do these probabilities using normal CDF just like before, but the key is the standard deviation is changing. So the bigger your sample size is, the less those means are distributed from the population mean. So the bigger your sample size, the more the data gets sucked in towards the middle. And so that's the big takeaway. So when you're doing these probabilities with samples, you have to take that into account when plugging in the standard deviation. So that's it for doing this with the sample mean. In the next section, we're going to look at doing this for the sample proportions, which we'll talk about then. Don't forget to do your homework assignments. And as always, if you have any questions, feel free to come to send me a remind message or an email, and I'll get back to you as soon as possible. So have a good one, and we'll see you at our next video lecture.